What's up, my students? I am Mr. Kim, and here's a video on intermolecular forces, as I have promised. So here we go. So in class, we talked about the difference between intra versus inter. Okay, we know intra means within, inter means between or among. We talked about several examples. Okay, so let's talk about intermolecular forces. So these guys, intermolecular forces are not bonds. Okay, we know that intramolecular forces are bonds. We talked about, why intermolecular forces are so important. This guy definitely needs intermolecular forces in order to climb around walls and save some insurance or save some money on car insurance. And we need intermolecular forces to hold hands with other people and to save ourselves from dangerous things occasionally. Okay, so there's three types of intermolecular forces. We briefly covered the first one, so let's just kind of start over. So we talked about dipole-dipole interactions, and this is when we have molecules with that demonstrates dipoles. Okay, so let's talk. So this molecule has a dipole. What does that mean? Okay, a dipole means that we have one atom in this molecule, okay, that's kind of hogging the electrons. These guys are sharing electrons, this atom versus this atom in a single molecule, but this atom just happens to be hogging the electrons closer to itself. So it's causing, a partially negative charge right here, whereas the other side, of course, will be partially positive. Yeah, this is sort of like when you guys eat Oreo cookies, right? When you do, what do you call that? I think it's an Oreo cookie twist with your friends, and you twist half of the Oreo cookie off, right? The person who really puts his or her heart into that twist motion will definitely have more cream after the Oreo cookie twist is done and over with. So you'll kind of have more of the cream to your side of the cookie. Okay. Oreo cookie shakes are very good, but this is not a video about Oreo cookies. So let's talk a little bit more about these molecules. So if these molecules exhibit dipoles, okay, dipole moments, and we have a whole bunch of molecules like that in a jar or wherever these molecules may be, we are going to have intermolecular forces between these molecules. Okay, we're going to have forces between these molecules, between. And these forces are forces of attraction. They're not bonds, okay? So because of these partially positive and partially negative sides to these molecules, these sides are going to attract oppositely charged sides of different molecules. Remember, these guys aren't charges. They're not actual charges. They're just partially positive and partially negative because the electrons are distributed more closely to this side. Okay, so this is just attraction. This isn't an actual bond. Okay, so these types of interactions exist, and it's especially helpful to think about, solids versus liquids versus gas. Okay, solids will have a stronger intermolecular force, hence they're able to stay solid, whereas gases have weaker forces, hence they're gaseous. Okay, an example of a dipole-dipole force is hydrogen bonding. So this is number 2 for our example. Hydrogen bonding also demonstrates the exact same concept of dipole-dipole interactions, but now we're talking about hydrogens. So if we have an electronegative atom such as oxygen and hydrogen bonded to it, we're going to have a very strong dipole where the electronegative atom is going to attract, the hydrogen's electron, slightly hard. It's going to tug on it a little harder. So we're going to have this dipole for this molecule. If you have a whole bunch of these types of molecules, right, that have hydrogen, we are going to have attraction between the electronegative atom of one molecule to the hydrogen of another molecule. And this is how water stays together, you guys. We have a whole bunch of water molecules here, and the dipole-dipole interactions are causing it to sort of stick. Okay, this type of interaction also happens in DNA, where we have hydrogen bonding occurring between our base pairs. This helps us to keep our DNA winded and coiled up. Okay, the last of our three intermolecular forces that we will talk about is this guy over here, London dispersion forces. But I want you to know two things about this. Before I even talk about what they are, the two main points for London dispersion forces are that every single atom and molecule have this potential. So every single atom and molecule have London dispersion forces. Okay. And also I want you to remember that this attraction is the absolute weakest type of intermolecular force. Okay. Now they're caused by instantaneous or temporary dipoles. And we'll talk about what that means. But think about what dipole means. You know what these are. They're caused by instantaneous or temporary dipoles. Okay. And how do we get these? It's caused by the movement of electrons. Okay. Temporary movement of electrons. We'll talk about why. So here we have some atoms. Okay. So we have atom A, atom B. Okay, in any given atom, let's pretend this is, it can be any atom, just whatever atom you want it to choose, you want it to be. This atom will have some sort of a certain number of electrons just, flying around in its orbitals. Okay, same with this electron. Okay, and its valence electron is just going to be somewhere here, right? Remember, electrons behave as waves and particles, so they're just kind of everywhere. Now, at certain moments, we're going to have electrons that sort of gather to one side more than the other side. So let's just say for this atom, the electrons, maybe they might be hanging out more to the left than to the right. If that happens, then this left side of that certain atom is going to have a partially negative charge, while the other side is going to have a partially positive charge. In this way, we are kind of creating temporary dipoles. And I say temporary because electrons are always moving. So they're not gonna stay here forever. But for that, that temporary moment where the electrons do happen to induce a dipole, we're gonna have attraction. Just like this type of attraction, but these guys are permanent dipoles. This is temporary. Okay. Now if we're talking about molecules, okay, we have a hydrogen molecule. Same thing, you guys. While they're sharing the electron, while these two hydrogens are sharing each of their electrons to create a bond, these electrons might favor this hydrogen more than this hydrogen, just because electrons are always sort of moving. Okay, so if that happens, if that temporary dipole happens, these hydrogen molecules will want to attract. Okay. Think about, when you go shopping, right? When you're thinking about something, you want to really buy something, whatever that may be. Maybe it's an Oreo cookie shake, who knows? But, sometimes you might be wondering, I shouldn't eat it because there's too many calories, or, I have a sports practice to go to. But, there's this, sometimes just for like a brief split second, you might think, no, I have to buy that Oreo cookie shake. I have to buy it, right? So there you just induce that temporary dipole that causes you to have more attraction for that Oreo cookie shake. Okay? But of course, later on you might not want to buy it. So London dispersion forces, you guys, are very weak forces. Okay? So just brief recap. We have dipole forces. We have hydrogen bonding, which is a part of dipole-dipole interactions. And lastly, we have London dispersion forces, the weakest of the three that we talked about. Okay, tomorrow we'll go over some examples in class. So it's been 9 minutes so far. So thank you so much for watching, you guys. I'll see you tomorrow.